All right, so good afternoon, everyone. Are you hearing me clearly? Hello, are you hearing me clearly? All right, so let's begin. So this is the worksheet that I sent in the group, I believe yesterday or the day before. So um, these will be taken from each topic that could possibly come on your paper two. So let me just scroll through it quickly. We'll go to the top. So this is on deformation. This particular question where you're required to plot a graph and you're also required to determine the gradient, give the information of what we can expect in the gradient. So let's go through this one in particular. Okay, let's just go through it quickly. So as I would have stated in class, for every physics CSEC exam requires a graph. So that's the mentality that we should go into the exam with. We don't know what the graph is going to be on, and we'll look at that in a few, right? Which questions the graph could possibly come from, so you can get your mind prepared for that or what to expect. The table one, the results obtained by a student who performed an experiment to investigate how the length of a string varies with the load applied to the end of the spring. All right, so are we all seeing the screen, right?
Yes, sir.
Yeah, good. Okay. So the first question says that you must plot a graph on page 3. Of course, that will be given. That graph leaf would be given. So come here. Yeah, so this graph paper would be given. So plot a graph of length on the vertical axis versus load. All right, so this is this yesterday kind of set it up a little bit better than what we do in the labs. In the labs, I don't usually tell you where to put the different quantities. I just say plot this versus this, and you know that the one that comes before, that's what we usually put on the y-axis. But here they give you they help you a little bit. So the vertical axis right here. All right. So let's say that we go ahead and we put up. Can I get up? All right. Shadow. I think you know what I'm going to do. We'll go through this quickly. All right. So I'll get a sample graph leaf and come back. Give me 1 second. I get a sample graph leaf and just to be thorough. Did anyone attempt it though? Remember when I asked
You left that out, sir, because I have a graphic.
Okay. All right, so here it is. I'm going to go from here. This is the original document. Um, done. Um, um, Right. Going a little further. Okay, perfect. Can you see this? Can you see the wording?
Yes, sir.
All right. So we can see that the we have length on the vertical and versus load. So when you go down here, our graph paper, bring up drawing. All right. So the first thing we'll do is identify which axes they would go on. Right. So what would you put on this axis? Let me go back up. What would you put on the y-axis?
The load, sir.
No, we would put length as vertical axis, right? So the length would go on the vertical. Vertical meaning the y-axis. So we'd go ahead and put length here, and then we know that load would go down here. So let's run through this quickly, right? Because some of us are already experts at plotting graph. So the first one, load starting at 2, ending at 10. So this is the process of plotting a graph in the shortest time possible. You look for the highest point and the lowest point. So the highest point would be 10 and the lowest point would be 2. For the length, the highest point is 0.51 and the lowest point is 0.36. So we see that it doesn't really start at 0.1, 0.2, and so forth. So that right there, we know we can cut the graph right here. All right, so zoom it in. Okay, try that. All right, so is that better? Right. So length would go on the vertical axis, and load would go on the y-axis, on the x-axis. All right. Good afternoon, Brandon. So right here we can see on the length it starts at 0.36 and it ends at 0.51. Right here we can see that we can cut the graph because it doesn't start at 0.1, 0.2, 0.3. Right? It goes straight to 0.36. So we can just make a note of that right there. We can cut the graph. All right, so the first point, let's bring up the axis now. So on the length, all right, let's do the load first. The load first. The lowest point was 2 and the highest point was 10. I would recommend we do for every centimeter we do, or for every 2 centimeters we do 2 newtons. So load, the unit for load will be newtons. So it go 2, 4, 6, 8, and 10. So we could do that way. Can we do it any other way? 2, 4, 6, 8. So if we do 4, it would be too much. So let's say that we did 2, 4, 6, 8. Would need one more to go to 10. And you know that falls off. So the best thing to do right here would be for every 2 centimeters, we do 2 newtons. So it would be 2, 4, 6, 8, 10 for every 2 centimeters right here. Now, as I always tell you, I don't recommend you ever using 3 centimeters. So never go here. Don't start at this point right here. Going 2, 4, 6, 8. Don't ever do that. Always use 2 or 4. Never do 3. What just happened?
Say it again, sir.
So
Say
never use,
use 2 or 4.
yeah, never use 3. Always use two or
Oh,
four
oh yeah.
centimeter. All right. Yeah. Everyone understand that?
Yes, sir.
All right. Anyone else want to confirm? Understand?
Yes, sir.
Yeah. So never use 3. Always use 2 or 4 because if you use 3, you're going to end up in problem when calculating the gradient. We're not going to be able to use the entire do the entire question because of time, right? So that would be for the load. Now for length, we see that it starts at 0.36. We can do 0. We can start at 0. Wow, there's an issue right here. I'll come to that next. So we can start at 0.3. So what we'll do, when you see it doesn't start at 0.1, so it usually 0.1, 0.2, 0.3. It goes straight to 0.3. So that means that it's telling us that we can cut the graph. Well, my apologies. What did it say here? So that messes up our plan, right? We can't cut the graph again because it says that we must start each axis at 0. I did not see that. Okay, so we're going to have to start each axis at 0 then. I did not see that. Okay, so let's do that at 0. So we can do 2 as well. So 0.1, 0.2, 0.3, 0.4, 0.5, maybe. See if there's a better way or one that we can get more out of it because 0.1 every 4, we could try every 4. So 0.1, 0.2, 0.3, 0.4. Yeah, we can do 4. So let's do 4. So for every 4 would be 1 meter. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. So we're looking at 0.1, 0.2, 0.3, 0.4, 0.5. So you realize that I didn't do 3. Always use 4 spaces or 2 spaces. Never do 3 spaces. Always use 4 or 2. If it's too big for the 4, then you use 2. If it's too small for the 2, then use 4. When we use 2 spaces or 2 centimeters, it stopped about here. That is just perfect in the graph. All right. Um, so go ahead and just attempt plotting these. So the first one is 2 and 0.36. So that's 2 newtons. 2 newtons right here. And we'd match that up to 0.36. So 2 newtons here, 0.36 up here. So it would fall, this is 0.35. So 0.36 would be here. The 0.35, 0.36 would be here. So this would be our point right about here. Our next point was 4 and 0.35. 4 and 0.35. So 4 is here, and we'll match that up. You don't have to draw the line, I'm just doing it for this example. 0.35. So basically we're matching up 4 on the x-axis, 0.35 on the y-axis. Next point, we would do 6 and 0.4. So 6 would be here and would match that up to 0.4. This one is easy. 6 on the x-axis, 0.4 on the y-axis. I think we have 2 more left. So 8 and 0.46. So 8 on your x-axis. What was it again? 8 and 0.46. 8 on your x-axis, 0.46 on your y-axis. So 4, this is 0.45 right here in the middle. 0.45 also would fall dead between 0.5 and 0.4. So it would be in this line. 0.46 would fall a little bit above it, right here. All right, so we see we're getting that straight line, even though there was an initial happening right there. I don't know how, what happened there. And 10 and 0.51. 10 and 0.51. So 10 would be here on your x-axis. You would match it up to 0.51. So this is 0.5. 0.51 would be a little bit above it, right about here. All right, so about here. So we're getting that straight line. So they told us to start from 0, start each axis at 0. That's why we weren't able to cut the graph. However, if we had, if we were allowed to cut the graph, then we'll get a much better looking graph that would spread across the graph paper, right? So it would spread across the graph paper nicely like this, right? But they told us to start at 0. So ensure that you read everything on your paper as well. Because see, if I didn't read that, then we'd lose the mark for not starting at 0. Maybe there's a reason why. Let's see. All right, so the next step, after we get our points on the graph, what would you do next?
Freehand.
Yeah, yeah, basically. So we call that the best fit line, right? So the best possible way that the graph will look. All right, so I'm seeing, and it should be a straight line. So I don't want anybody doing, well, you have some questions that will give you a exception. You have some instances, but most of the time you'll be, I don't want to see anybody like doing this, right? No, you're not able to get a gradient from this. Any question that asks you to get a gradient, look in the question. If there's any question that asks to get a gradient, you should not do this. All right, you should get a basic line. So this question asks you for a gradient. You should do a basic line, meaning a straight line. So I also make sure that you carry a ruler. It will help you. If I had a this might not look so neat, but I'll see what I can do. Right, getting that. All right, so it might not be straight, but carry a ruler. Carry a ruler so that you can get a straight line. So from this, you're able to calculate the gradient. When going ahead to calculate the gradient now, you can choose between the first 2 points. You can draw a triangle between the first 2 points and the last 2 points to get your triangle, right? So after you get the gradient, you always go, you can also go down here. Yeah, let's go down there. So between, I always say when you're doing a graph, go between the first 2 points, which would fall about here, and your last 2 points. I always say this. All right. So this should line up here. Of course, this would look much more neater if I was using a ruler. I'm doing all this freehandedly, so it is very untidy. All right, so let's take this one down here. Let's use this one. Going down. So you draw these dotted lines to help you to get the exact points that you're working with. All right, so what is the formula for our gradient again?
Rise over run.
Could you repeat?
Rise over run, sir.
All right, so gradient is equal to rise over run. All right, so what does this mean?
The vertical side of the triangle coordinate and the
Yeah, but break it down
rise
in
would be
equation. Break it down into equation that we always use.
x1 minus y1.
No.
I'm not
Try
sure. I
again.
remember it. I remember
Rise. Which one is the rise?
the y, sir.
The y. So that
Y.
would be the difference between the y, right?
Oh yeah.
So what would it be now?
So y1 subtract by y2.
It will be the other way around. So y2 minus y1. If you do y1 minus y2, you get a negative value. We don't want that. And then for the run, what would it be?
x1 minus x2 minus x1.
All right. So x2 minus x1. So rise is y2 minus y1. Run is x2 minus x1. All right. So whenever you ask you for the gradient, if you literally just state this, I get a point. All right. If you like write down, if you don't know how to do a question, and write down the equation, you automatically get a point. Are you hearing me clearly? Am I breaking up in at all? By the way.
Yes, sir.
Okay. All right. Yeah. Internet is a little bit unstable. Sorry about that. Okay. So y2. So what would be the value for y2 now? What would be the value for y2?
Um, uh, 0.3. No.
All right, so I'm going to ask the first thing now. For the grade for y2, will it be A or B? Which one did you use for y2?
A, sir.
All right. So
B.
A,
A.
exactly.
Why
Yeah,
two, sir?
yeah. Because it's the one. That's it. That's the second point. That's the last point. All right. That's the last point. That is closest to the last point that we plotted. This is closest to the first point that we plotted. So this would be y2, y2, and this would be y1. This is um, this is deformation and plotting a graph. So Hooke's law. All right, length and load. Okay. Hooke's law. When you increase the load, you increase the length. Remember that same graph that you plotted in your that I asked you to, or that was it that I asked you to plot in your
Yes, sir.
lab. That same graph, yeah, same basically the same thing coming for this exam, or the same thing came for this particular exam. Not saying that it will come on Monday. Just saying that is a similar things. All right. So this would be y2 at the top, and this is y1. All right. So this is length. As the length increases, well, as the load increases, you can see that length increase. Okay. So y2, we'll have to find out the individual points. So this, as you said, this was 0 0.4. This is 0 0.45, 0 0.45, and then 0 0.45, and this would be 0 0.46. This would be 0 0.47. This would be 0 0.48, and then this would be 0 0.485 because it falls in between 0 0.49 and 0 0.48. Let me go over it again. So go over the whole process. All right, we plotted our graph, right? Plotted our points, we draw a basic line. Now we're finding the gradient. The gradient falls between the first 2 points and the last 2 points. The first 2 points would be somewhere about here in between these two. Any point, but you really can use any point on the line, but I recommend between those 2 points since it is they are far apart, moderate distance apart. So the line comes here. You're going to find this particular point. This particular point, you would use y2. Y2 down here. So Y2. I'm sorry for the lines because I'm not using a ruler. I'm using freehand. So this is 0.45 because it falls between 0.4 and 0.5. 0.45, this would be 0.46 right here. Let me kind of zoom in a little bit for you again. Um, let me zoom in again. So this is 0.4. This is 0.45. This would be 0.46, 0.45 right here, 0.46, 0.47, 0.48, right? Just give it a trouble. So using this particular line. So 0.45, 0.46, 0.47, 0.48, this is 0.49. The line falls here though between 0.48 and 0.45. So therefore Y2 is equal to 0.485. You could roll it up to 0.49 to make life easier, but I recommend you write out the entire thing. Be as exact as possible. Now down here for y1, the second triangle comes here. This one is also here. So 0.3, this would be 0.31, right? 0.31,
Yes, sir.
0.31, 0.32, and 0.33. So it falls in between again.
Yes, sir.
So 0.2, it falls between 0.32 and 0.33. So therefore, y1 would be what? 0.325. I am being very thorough, right? I am being very
That's
thorough.
why. Y1.
Yeah,
That's Y1,
y1.
sir.
Yeah, y1. Let me
B
write
so
it.
B is Y1. A is what I. CM fee. I.
Yeah, it's the same concept for x now. We're going to x. So x, now let us zoom out. So x is very easy, right? X is very easy now. So which one would be x2? Let me just write C and D. Which one would be used as x2? C or D?
C, sir.
Exactly.
D.
It would be C because that's the last one that we plotted, closest to the end. All right. It would be down here. So C would be your x2. No, sorry, D. So down here would be x2 and down here would be x1. So what would be the value for x2? This one is very easy. So you
9,
can
sir.
yeah, so this would be 9. It falls between 8 and 10. Simple 9. All right, so x2 would be 9. And what would be x1?
3.
Yeah, so x1 would be 3. So you see, it's really those decimal points really difficult and it will take practice. That's why I ask you to get between now and Monday, get the same example and plot it over. Plot over the same example. That's the only way you're going to master this by practice. That's why we practice it in the lab. That's why I gave you a lab with it. I told you to plot the graph in it, right? Only probably a selected few plotted the graph. The moderator came and she said that the students in the plot the graph, I can't really give them a mark if they don't plot the graph. You have some students' marks went up in the labs, right? And it's because they did effort. So only a few selected students plot the graph. I can't really help them out then. Because she saw the grades, right? And she's wondering how can she help? And she couldn't help because there was nothing to help. There was no way that she could help. But for you, you can help yourself now by getting the graph paper between now and Monday. Plot over the same graph. You can do it one time, you can do it 2 times, you can do it 3 times if you really want to take this seriously. Because a graph will come. All right. So y2 we said is 0.485. Y1 is 0.325. So let me zoom out a little bit for that. So y2 is 0.485. Y1 is 0.325 and x2 is 9. X2 is 9 minus x3. X sorry, no, x2 is 9 minus x1 is 3. All right. Can someone plug this into the calculator and tell me what you get, please? So that's 0.485 minus 0.325 over 9 minus 3.
So 0.4 you get 5. 0.325 and 16.
0.16.
Yeah, 16. 0.16.
0.16. That's what you said?
So your answer is going to be 0.0.
Yeah, but what to this should be 6. The final answer is 0.22.
No, 0.027. 27.
27.
Yeah.
Could someone confirm this, please?
Yes, sir.
All right.
Yes, sir.
All right. So the gradient is equal to 0.027. All right. So the gradient was the question. The next question now. All right. So I'm going to give you. All right. You know what? I'm going to screenshot this and paste it in the group. So I'm going to ask you one more time to get the graph paper between now and Monday and practice doing this question. Try and get the same results that we got here. Okay. So gradient 0. All right. So there's another question now. So we're going to try that question. The question asks us determine the gradient of the graph. We did that. Let's see, that's 4 marks. Right. See how heavy that is? 4 marks. And the one before that asked us to plot on page 3. So the plot in the graph is 7 marks, heavy. And then determine the gradient. M equal y2 minus y1 over x2 minus x1. By just stating this, you get 1 out of the 4 already. By just stating this. All right, that's the beauty of physics. All right, so all right, what do you remember about Hooke's law? What is the formula for Hooke's law again? So F is equal to what?
So I went with the spring, though.
Yeah.
I went with it.
The spring, yeah. All right. F equal
The
to
normal.
all right. So F equal kx, right?
Yes, sir.
Okay. So what was the question asked what information about the spring does the gradient of the graph provide? Does the gradient of the graph provide, right? What information? All right, so what are we looking at here? The gradient of the graph, let's go back. The gradient is equal to change in y over change in x. What was the y again? Y was length, right?
Yes, sir.
And the x was load. or force. So length over load. How can we how can we get um, length over load here, or x over f right here? What can we do? X over f. How can we get x over f for this question?
F time X. No, K.
Sorry about that. My internet went. Are you seeing the screen? Let's do that check.
Yes, sir. So
Are
we're
you
gonna
hearing
have
me?
F divide by K.
All right, so we could start out with f divided by k. Remember, the final thing we want is x is kind of x over f, right? So we could start
Yeah,
out with f divided by k equal x. So we will do here.
X.
Then what would we do next then? We want x over f.
Um, divide. No, yeah. No, what? Yeah, we divide by same a K over F.
All right, so we divide. We say f is equal to kx.
Yeah,
Right? We want x over f. We want x over f now. All right, and then we divide both sides by k. We now have f over k equal x, but we want x over f.
F.
So what we do, we bring down this f right here.
Yes, sir. So you could do this way, sir, by put K over the top instead, and just bring over it,
That that would be long. That would be
K
long.
over R. Okay.
Yeah, that would be long. That would be long. So we get 1 over k is equal to x. My apologies. X over f. So the gradient, we get the gradient right here. This x over f would be a gradient. Therefore, the gradient represents the inverse of the spring constant. All right. So this k represents, remember that this represents the spring constant, x represents extension, f represents the load. So the gradient now represents the inverse of the spring constant. Inverse just mean 1 over the quantity. All right. So um, what information about the spring does the gradient provide? The inverse of the spring constant. Right? Inverse of the spring constant. Let me screenshot this as well. All right, so we won't do some of these questions because we did them in class already, right? Um, so is it okay if I stop sharing now?
Yes, sir.
All right. Anyone need me to stay on the page for a little while, or you want me to go back to something?
Oh, sir.
Okay. So I'll post the um the the screenshots in the group now, so you can get them.
Wait, sir. This alone I got you today?
No, I have we just started. Then we start again. 1:40. So I said 1.5 hour. So we should have about 40 minutes left. Yeah, right. Oh my god. Alright, so I'll post them in the chat now quickly, and then we move on to the next question. Um, 120. Okay. All right, so it is uploading. Let's move on in the meantime. All right, you should get it now. Next question. All right, so we finished the formation. Okay, before I continue, let me show you that one more time. All right, so these, if you go back to the WhatsApp chat, right? I sent this inside the WhatsApp chat. These are the topics that will be coming, or selected topics that you should focus on. They will choose out of which one they want to use. Great. So we did in class, right? If I remember correctly, the first one here is graph work. Simply, let me go down here because I'm very slow. Right, this is much better. So the first one, graph work and analysis of data. So we just did that, right? Graph work, plotting a graph, finding the gradient. All right, we just did that a while ago. We did deformation as well. But deformation is just Hooke's law, right? Turning forces, we did that in class as well. We did temperature, we did gas laws, the types of waves. Did we do speed of sound? Don't remember. I have to check this again. But I'm sure we did reflection, refraction, critical angle, alternating current. All right, so we have some of these to cover. We won't be able to cover all of them today. What we'll focus on is particles in an atom, radioactive emissions, and motors. All right, that's what we'll try and focus on today. So that means that you'll have to do readings, go back to your notes on these. So electromagnetic force. I'll see if time allows you to do magnetic force and half-life. If time allows. Right? But it's quite a lot to cover. All right. So as I was saying, the the questions that can come with a graph, with the topics that can come with a graph are deformation, gas laws, so your Charles law, Boyle's law, pressure law, and so forth. Refraction can come with a graph, just like what we did in the lab. Just like what we did in the lab, where we had sine I versus sine R. So I took out the graph. Go ahead.
So, yeah.
Yeah, I took out the graph component because I realized that there were a lot of persons who didn't do it, so I didn't mark for the graph. All right, but it was initially intended for you to do the graph, but I took it out because majority of the persons were not able to do it. But it like practice, go back to refraction. All right. So what we'll do now, looking at now, is motors, right? We'll be looking at motors. So let's go through this. So as I said, these are questions that I would have given you already in class. So we talk about the formation, turning forces, we did this in class. So go back through these. We did temperature, Boyle's law, gas laws, and so forth. Right. We also did this. So we'll focus on motors today. All right, so this question states that figure 3 shows a diagram of a simple DC motor connected in a circuit, right? So with reference to DC motor shown in figure 3, explain how coil is able to rotate continuously. All right, you know what? I'm going to go straight to your notes. No itching. No itching. We're going straight on to your notes that we discussed. So what is a magnetism? All right, so this is our Google Classroom here. All right, are you seeing the screen?
Yes, sir.
All right, so
Yes, sir.
classroom and magnetism. All right, so scroll down. We go all the way down here. It's all the way down here. Okay, DC motors. So a simple DC motor, we just go through it quickly again, right? Simple DC motors, current through a coil which is immersed in a magnetic field, produces forces in accordance with Fleming's left-hand rule. Very important. So if you remember, we have Fleming's left-hand rule and Fleming's right-hand rule. Remember correctly, right? Give it a second. I think Aldre is joining. Let's give him a second. So he's taking out a while. Let's continue. So Fleming's left-hand rule. Since the current flows in opposite direction in either sides of the coil, the forces are in opposite direction, and the coil rotates about the axle. All right. So reading all this, I just have to go ahead and explain it, right? But before that, let's go back to Fleming's left-hand rule right here. So Fleming's left-hand rule states that, let me just move this, states that the thumb represents the thrust or motion, the index represents the feel, and the middle finger represents the current.
So this is a must on the
Yeah, like depend what we're seeing here. Why is this not able to join? Oh, what we're seeing here is that you have magnetic forces and you have electromagnetic forces. So Fleming's left hand rule is a must. Fleming's, you have to.
Afternoon, sir.
Good afternoon, afternoon, Pavan. Right. So Fleming's left hand rule is a must. You have to know it. Have to know it. It's a must. Fleming's left hand rule. The thumb, it goes. I am 75% sure that Fleming's left hand rule is coming. I am 80% sure that motors are coming. You have to know how to explain motors. All right. So the thumb represents the thrust. The feel is represented by the thumb, by the index finger, and the current is represented by the middle finger. Okay, let's go through that now. So I'm going to switch on my camera. All right. So you have the thumb representing the feel, representing the thrust. You have your index representing your feel. Thumb represents the thrust or force. Index represents the feel, and current represents the motion. The is represented by the middle finger. All right. Thrust, feel, current. Let's go to the question now. So before let's do this example. Um, so before we go to the motors, let's do this example first, right? So you have this particular one, this particular no, not this one, right? Fleming's left hand rule to verify that thrust or force on a current conductor. So you have current. Remember that whenever you have the X, let me annotate. Okay. Remember, anytime you have the X here, it represents into the paper. Anytime you have the dot, it represents out of the paper. The X into the paper, the dot out of the paper. So for this current conductor, where is it going?
In I paper.
All right, so it's going,
inside.
yeah, it's going in I paper, right? So let's try that. Um, so basically towards your computer screen or towards your phone screen. So I'm going to ask you to point towards your phone screen. Can you turn on the cameras if you can, just so that I can see that you're doing it correctly? All right. If you are able to, if you're not able to, that's fine. But it practice is always good. So your current is going into the paper. The magnetic field is always going from north to south. Remember that, please. North to south, always. Magnetic field. So remember that the current is represented by the middle finger, the field is represented by the index, and the force is represented by the force
Wi-Fi.
the force is represented by your thumb. So we're going to do this example. So the current is going into the paper. So remember that the middle finger is the current is going into the paper, so towards your computer screen. The current, the field is going from left to right. So from north to south is going left to right. All right, and where's the thumb pointing now?
North.
All right, so it's going up, it's pointing upwards. So therefore, the force would be upwards. We'll go over it again. The middle finger represents the current. The index finger represents your field. The field is always from north to south or wherever indicated. North to south, the north pole to the south pole. And your thumb represents the force. So you have your current going into the paper towards you. The field going from north to south is going this way. And you have the force, which is the thumb, represented going upwards. I would love if you could turn on the cameras so that I can correct you if you're wrong or confirm if you're doing it correctly. I would appreciate that. All right. All right. Also, remember, if the current is flowing in this direction, as you can see in this example, if it's flowing that way, then you know that no thrust or force, because the current would be moving parallel to your field lines. The field lines would be here. They would run in from north to south, and the current is moving with them. So there would be no thrust or force. Let's do one more. One more. This one here. No, let's do this one. This one here. So the current, it says that the current is a dot right here. So this means out of the paper. Out of the paper. Remember, the middle finger represents the current. This index finger represents the field. And this guy up here represents the thrust. So here the force is going to go. So you have the, all right, so let me ask Walden if he's having trouble with Zoom or Aldre.
Is it?
Are you having problem with Zoom or it's just the Meet? It's just
The internet, sir.
the internet. Is the internet?
Yeah, yeah.
All right. Please let me know if you would prefer Meet.
No, that good. I
All right.
intend.
Okay. Because if I was using Meet, I wouldn't be able to write on the paper like this. All right. That's why I used it. I use Zoom. All right. So, where was I? Right. So I was saying that the middle finger represents the current, this represents the field, and this represents the force. Okay. So the current is going out of the paper. So current, you would point your middle finger towards yourself, right? Like this, point it towards yourself. The field is going upwards. The magnetic field is upwards. So while your middle finger is pointing to yourself, the field is going upwards. I would love if you could turn on the cameras so that I can see if you're doing it correctly. Please practice this while I'm doing it. So your magnetic field is upwards. The current is coming out of the paper, and you can see that the thrust or the force represented by the thumb is going in which direction? Where is it going?
Repeat that, sir.
Let me go over it again. So you have the current. Where's the current going? in this example right here. This one.
To me,
I'm not hearing you.
out of the paper.
Yeah, so it's going out of the paper because it's represented by the dot. Where's the field going?
Not.
All right, so it's going upwards as well. The field is going
Okay.
upwards, north to south. All right.
Not this.
So the see my middle finger is represented by the current. It is pointing towards me. The field is going upwards. So the force will go towards the left. Do we see that?
Yes, sir.
All right. Field is going towards the left. All right. So let's try this example now.
Sir, I kind of understand that one.
You're not getting that one?
No, I don't understand.
All right. Let me try this one. Let me go over this one again. This one right here. Where is the current going? Where's the current going for this one?
Into the paper.
All right, so you point your can you turn on the camera? Is it possible for you to turn on the camera?
No, my computer may use so the camera no the panic.
All right. So the current is going into the paper. You would point your middle finger towards the screen. So do that quickly. Point your middle finger towards the screen
With the left hand.
with your left and right.
Yeah.
The field, you would use your index. You would point that from the North Pole to the South Pole. So it would go like this. So you'd point it this way, while your middle finger is still pointing towards the screen.
Oh, yeah.
Where does your thumb point? No, where does your thumb point?
Up.
Yeah. So that would mean that the force would be upwards. Force would be upwards. You see that?
Yeah.
All right. So let's try this one now. So your where's the current pointing for this example? To your right.
Out of the paper.
All right, so it's pointing out of the paper. You would point your middle finger towards yourself like this. So see to your middle finger, you'd point it towards yourself.
Yeah.
Then where's the field going?
To
Up.
the left.
No, it's going upwards. So it's going from north to south. Always. Field goes from north to south, right?
Yeah.
So you'd point that upwards. So while your middle finger is here, you'd point your index finger upwards. When you stretch out your thumb, where does it go?
To my left.
To the left.
Exactly. So it goes towards the left. So that means that the force would be in this direction. All right. Is that better?
Yes. Sir.
Yes, sir.
All right. So let's go down now to the example with our motor now. So it's the same example that we saw in the question, right? So we're looking at the left hand side first. We can see, let me see if I can zoom in a little bit. Where's the zoom icon? All right. So we're paying attention to the left hand side here. All right. So where does the left hand side like it's going? Where is it pointing?
Up.
Into the paper or out of the paper?
In.
Yeah, it's pointing into the paper. And where is the right hand side pointing?
Out of the paper.
All right, so it's pointing mostly out of the paper. They turn it like that so to give you perspective. All right, but it's really out of the paper. All right, so we would go ahead and do the same exact scenario. Where is the magnetic field pointing?
Up, sir.
No, this is the North Pole, this is the South Pole.
So side
All right, but you have to give me exact directions.
to the right, sir.
All right, so it's going from left to the right. Do you see that?
Yes,
All
sir.
right. So what does this one represent again?
Current.
All right, so current. What does this one represent again?
The field.
What does this represent again?
Ethers.
Okay, so we have the current. Where's the current going?
Wait.
Think about it.
In.
All right, so
Not in.
the current is going into the paper. Perfect. Right. So you'd point your middle finger towards your screen.
Yeah.
All right. Where's the field going? Where's the field going?
Up.
To the right, sir.
Remember that we said that the magnetic field is going from north to south. So it's going to the
Right.
right. Perfect. So where now is the thumb pointing?
Downwards.
Down. So where's the force now?
Down.
The force would be downwards. All right. Do we see that?
Yes, sir.
Everyone see that?
Yes.
Anybody want to go for it again?
Yeah, go right again.
All right. Even though my hand is hurting me, I'll go right again. All right. So let me clear all. What is this? Let's go right again. So where is the current going for the left hand side? The left hand side. Where's the current going?
Into the paper.
All right. So let me just write that down. Left hand side.
To the right.
Pavan, what happened to DeMarco?
No, sir. Probably. Am I asking?
Yeah. Because if it's a case with Zoom or nobody's telling me if they have a problem with Zoom. So I have to assume that everything is good. If you have a problem with Zoom, let them tell me, please. Because I can switch over. It's just that I like to write on the screen like this. I'm not able to write on the screen like this with Meet. Zoom gives me the freedom to write on the screen. All right. So we need to hurry up and wrap this up, right? We don't have the whole day, and you need time to settle down and so forth. So, left hand side going into the paper, we would point our middle finger towards the screen. Do you see that?
Yeah.
All right. So it's going into the paper. This represents our current. The field goes from north to south. So we point that, we turn it north to south, and then where our thumb points, our thumb would point downwards. So we see that the force would be downwards. Let's do the right hand side. Is the opposite, right? Where we have the field still going from north to south. However, where's the current going?
Out.
All right, so the current is going outwards. Current is going outwards. So this represents our current, if you remember correctly, right? We would point that towards you, towards your forehead, if you have to remember, right? Yeah, do that. Yeah, because you can easily turn it. All right. So when I come to the exam, I must see people with this on the forehead. All right. So pointing towards you, the feel is still going from left to right. So where is the force now? So try it. Current coming out, the feel going from left to right, just the same.
Down.
Downwards.
Yeah.
Ensure that you're using a left hand.
Upward.
All right. So current is coming out of the paper. Um, the magnetic field is from left to right, and the current is going upwards. All right. So we can see if the left hand side, let's say that this is an axle, the left hand side is going downwards, the right hand side is going upwards. It would be looking something like this. All right. Okay.
Yes, sir.
Yes, sir.
Next aspect of this, so that would be 3 marks for me out of 6. I don't remember exactly how much the marks are. But the next part is that when you have no, this was the black side and this is the red side. The red side was on the left in the first example, A, right? A down here, right? No, the red side is now on the right hand side, but the direction of the current is still the same. The direction of the current is still the same
Mm.
because of the split rings. The split rings allows the same amount of the same terminal of the battery to hit the same part of the coil or different parts of the coil. So the red part was on the left hand side, the positive was over here. Now when the black was on the right hand side, but it was negative. When they switch positions, this side is still positive because of the split ring or the commutator. Please remember that would be an additional 2 marks right there. Looking out for that. All right. Do we see that? So the left hand side will always be positive, no matter which side is on it. The left hand side will always be positive, and the right hand side will always be negative, no matter what. All right. Okay. So let's move on.
Yes, sir. In saying Wi-Fi now works.
Okay. Okay. All right.
Mine to a data me have to use.
You have to be using data.
Yeah.
All right. Use flow.
Yeah, flow.
All right. So I think I will post on YouTube the recording so that you can. I think flow is more lenient with YouTube. Flow is more lenient with YouTube. So they don't use that much data on YouTube. All right, and it's better. Okay, so that is for motors. All right, so the positive side will always be on the left. So you have the red part of the coil, and you have the black part of the coil. The red side was on the left hand side, it was positive, right? The black side was on the right hand side, it was negative. When they switch positions, the black side is now positive and the red side is now negative. So it doesn't matter which terminal, right? No matter which side of the coil, the left hand side will be positive and the right hand side will be negative, just to keep that same motion. So it was anti-clockwise here. It is still anti-clockwise when it is rotating. All right.
Yes, sir.
So that is good. Let me see. Give me 1 second. Let me check the syllabus for one thing before I continue. If I'm missing out anything. Looking for. I'm looking if we're going to get AC generator.
I'm driving rain.
Yeah. So we're just going to get. Well, that is what I'm seeing here. Let me show you. So in the syllabus, right, we're just getting motors. So you have electromagnetic force, so that resolve current conductor within a magnetic field. Are you seeing this, by the way? Or it's too small? Let me.
Yes, sir. Message.
All right, let me fix that. Yeah. So electromagnetism. Well, magnetic forces. It should have a syllabus. I'll send it in the group again. So go back to this. So you must investigate the forces between poles. That's very easy. Come on. So two strong magnets, like poles. What if you have two north poles? What will happen?
Then push.
All right,
Yeah,
so
they not
they
repair.
repel
Yeah.
exactly, and unlike poles,
We're going to trap.
exactly. So define a magnetic field. A magnetic field line indicates the direction of a magnetic force acting on a north pole. So we go from north pole to south pole. Map magnetic fields. Um, we can do that quickly. So around a strong magnet, right? Remember, we go from north. Let's say that the north is here, and the south is here. You have the magnetic field looking like this. Very important. This is for a single magnet. So it will go from the north pole to the south pole.
Yeah.
All right. Your notes have a much better drawing than what I have. Let me show you. So go back to Google Classroom. Yeah, this one here. Here it is. Let me see. I got a better one. Yeah, so you can see that it. Can you see this? The screen?
Yes, sir.
Yeah, so it goes from the north and it feeds into the south. It does that on the other side as well. So it does it on the other side, but I don't know why they didn't bother to do this one as well. So it feeds around here. It goes from north to south, always, always, all the time. North to south, north to south. Okay. Um. Also, when you have two magnets, it will look something like this. Let me scroll up. So they said a single magnet, and they also said two magnets. So these two magnets here, where is it? Again, right, right here. You have two magnets right here. You have north feeding to south, north to south, north to south. and there are a few magnetic field lines that feed into its own. So you have that to look at as well. So check back in the notes, go back to and that. Also I'm going to show you again, right? So go back to your right hand grip rule. Right hand grip rule where if you had, remember this, where you had current moving in that direction, your thumb would point where the magnetic field is and you'd wrap your hand around it.
Yeah.
Yeah, that one. Fleming's left hand motor rule. Identify factors that affect the force on a current conductor and a magnetic field. So the strength of the magnetic field and the magnetic field of the current. So if you have a magnetic field within a, if you have a current conductor within a magnetic field, if you increase, if you have stronger magnets, it will be a greater force. If you have more current, it will be a greater force as well. So motors, this topic here on motors, the only thing, thank God, the only thing that they say will be coming is the action of DC motors. That's what they say. So, if they had the induced EMF, I'm going to check back. Let me check quickly. It can't really trust CSEC, so you still have to study AC generator because I still can't trust them. Because I think they did that for the chemistry exam where they said something was not going to come and it actually came. So I implore you to go through that as well.
Metals.
Yeah, you remember. So they said that only non-metals will be coming and the metals came, something like that.
Yes, sir.
Mm-hmm. Yeah, man. So you have to still be mindful of that. So they might say that is not coming. But I'm not seeing induced EMF. All right, I'm not seeing induced EMF. Okay, next thing on the agenda. Will be finished soon. All right. All right, so this is alternating current, a part of the same question. Thank God. Let me find it. So remember the commutator, right? The commutator splittering helps you to keep the same voltage on both sides. So just remember that. Keep that in mind. There's a question that came on that one here. What is the purpose of the splittering? Remember that it is used to keep the voltage on the same side. Please write that down. Commutator. The purpose of the commutator is to keep the voltage on both sides of the coil the same, or to keep the voltage on the left hand side the same and also the right hand side the same. All right, so with reference to DC motor shown in figure, explain how the coil is able to rotate continuously. All right, we just did that. We looked at Fleming's left hand rule, the fact that the force on this side based on Fleming's left hand rule. Please make notes of this. The Fleming's based on Fleming's left hand rule, the left hand side went down while the right hand side goes up, right? Giving you that anti-clockwise motion. All right. However, when between the splitting right here, you will have momentum of that motion allowing you to continue spinning. So even though while it's connected to the split ring, right, or the commutator, right, it's connected to the split ring and it causes the force to go down. In the middle right here, there's a slight slit. There's a little slit right here. In that, there's no force really, there's no current. However, the momentum of it spinning will cause it to continue spinning. Okay, move on to the next question now. Um, Trying to cover as much as possible in this session. All right, so the waveform shown in figure 4 depicts the current through a resistor connected in an AC circuit. So calculate the period and frequency of the alternating supply. All right, so we see types of waves, alternating current coming here. One second. All right. What would be the period of this waveform right here? Remember we said that the period is the distance between
Number cycle divided by time.
number cycle divided by time, all right? But what represents one cycle? That's correct. What represents one cycle?
From 0 to 30.
So 0 to 30, perfect. All right, so 0 to 30 right here to here would be one cycle. Also, from crest to crest would be one cycle as well. That's true.
No.
It would be from
Yeah.
crest to crest would be one cycle
Oh yeah. Yeah, I see.
or one wavelength. All right, and also from trough to trough down here. All right.
Yeah.
So the first cycle would be from 0 to 30. That's perfect. From here, it would go through one cycle, start again here. Up, down, start again. Up, down, start again. All right. So one cycle from here to here. One cycle. So therefore, what would be the period?
The amount of time we alternate between the
15.
15. No. Remember that the period is the amount of time for one cycle. One cycle is from 0 to this point. So what would be the period?
sir 4.
No.
1, 2, 3. 1, 2, 3.
Stop guessing.
None, I guess. One. I caught me. Did I count?
So one cycle is from here to here. So the period would be from here to here. Remember that this is time down here. This is current.
Yeah.
So
And wait, sir.
hmm? So
it just say period.
the
So my
period
box out it.
the period would be 30, right? Do we see that? The time it takes to complete one cycle. So the current goes starts from 0 to 4. Remember that this is alternating current, is a topic that will be coming or possibly coming.
Mhm.
The current would be from 0 to 4 and then to -4 and then back to 0 again. And the alternating current changes direction. So it goes, say we're in Kingston, or say that we're in Trelawney, and then the power plant is in Mobe. The current would go from Mobe to Trelawney and then back to Mobe again.
Mm.
So it would go to Trelawney, all right, and then back to Mobe. So it would go to Trelawney, it would reach Trelawney about here, and then go back to Mobe, right here. All right, so Mobe to Trelawney right here, and then Trelawney to Mobe right here. You can look at it that way. So the time it takes to do that completely, to go from Mobe to Trelawney, so Mobe, Trelawney, and then back to Mobe again, would be 30 milliseconds.
Oh,
All right.
yeah.
So the period would be 30 milliseconds. You see how fast that is? All right. Now, if you remember the formula for frequency now, frequency is what? 1 over period.
The number of cycles divide. Eh?
Yeah, number of cycles divided by time or divided by the period.
Divided by
Yeah, but in this case, the number of cycle would be 1. 1 cycle.
yeah.
Yeah. So frequency is the number of cycles divided by period. The number of cycles is 1. So it would be 1 divided by period. All right. So let's go ahead and do that. It would be 1 over 30 milliseconds. Milliseconds would be times 10 to the -3. All right. Could someone work this out for me, please? I'm going to try and finish by 3 o'clock.
uh 0.000003.
1 divided by 30 times 10 to all right, let me 30 times 10 to the -3 would be 0.0. So 1, 2, 3, 0.03. So 1 divided by 0.03. How much do you get? I am barely hearing. Could you repeat?
I got 33.
Yeah, 33.3. All right. That is correct. And remember that frequency is in hertz. All right. So remember to go through your standard form as well. Remember that 2 times 10 to the third power is actually 2, 1, 2, 3. So go back to your standard form again. So you can watch some videos on it, do some practice. 2 times 10 to the negative 3 would be negative, you would be going to the left. So it would be 2, 1, 2, 3. So 0.002. We can do some practice on this. All right. So yeah, your correct answer would be the period would be 30 ms and the frequency would be 33.3. Okay. I think I see a message in the chat. You're not able to see. Who is tablet? Who is fire tablet? All right. So you have to watch over the recording because we're trying to finish up. Never mind. All right. Watch over the recording. So the next question asks us to determine. Did you write this? Did you write this off? Can I erase it? I'll screenshot it.
Sir, one question.
Go ahead.
The frequency, I said 30 times 10 to a negative.
Yeah.
Yeah. Why we're gonna fit like all like questions that might come with AC power when we get frequency to calculate with the time with times 10 to the third.
Negative 3.
Yeah.
It's because the milli right here. So milliseconds. You might see milliseconds is times 10 to the negative 3. Milli.
Oh.
Yeah. That is way back in grade 10. All right.
Okay.
Way back in grade 10. So milliseconds has to do with times 10 to the negative 3 and so forth.
All right.
Mhm. All right. So the question asks you. Okay. The question asks if the resistor is 45 ohms, determine the peak to peak voltage across the resistor. All right. So first to we need the peak current. What would be the peak current? What do you think would be the peak current?
4 amperes.
All right, so the peak current is 4 amperes. All right, and then we'll go ahead and calculate the peak voltage. Now, what formula would you use to calculate voltage? Hmm? Could you repeat?
Current times resistor.
All right, so voltage is equal to current times resistance. That's good. So V equal V equal IR. So what is the current again?
4 amperes.
4 amperes. And then the resistor would be what?
45 ohms.
Times 45. How much do you get there?
180.
So 180 volts would be the peak voltage. However, peak to peak would mean the total voltage between this peak right here and this peak right here. So it would have the same shape. It would have the same shape like this one. So it would look something like 180 up here and negative 180 down here below the zero line. It would go up, down, and so forth. So the peak to peak would be from here to down here, the total amount of voltage. So all we just do is just add 180. So 180 plus 180, how much do you get there?
360.
Exactly. All right.
Mhm.
All right. So can I move on? All right, take it. You're taking it down.
Okay, move on, sir.
Anyone else?
Can go ahead, sir.
All right. The last question right here would be the maximum power. What is the formula for power again? What is the formula for power?
So you can go over that one more time, please.
Which one is that?
The one where like it just finished.
The resistor? That will be 2.
Yes, sir.
Yeah, who is this again?
Blake.
Blake. Just wake up.
No, sir. Me depending on long.
I mean, like, because your voice sound like you just woke up. You don't sound like yourself.
My up from like military depending for 9-1.
Okay.
Yes, sir.
All right.
Me name
So,
fire.
yeah. So, we want to find the voltage. Voltage is equal to IR. The highest current or the peak current would be 4. 4 right there. And the resistor is 45. Give me 1 second. Oh my god. Give me 1 second. All right. Sorry about that. So the peak voltage, well, the peak current would be peak current would be 4 amps. Now we want to find the peak voltage. That would be I times R. Peak current would be 4 times R would be 45. This would give you 180. So 4 times 45 would give you 180. Now the peak to peak voltage would be the basically the distance from here to down here. So it would give you the same shape as the current. So this would be 80, positive 80, this would be negative 80. And it would look something like this. So the peak voltage would be from here to down here, peak to peak. The total 180 plus this 180 down here, all of that would be 360. Do you see that? All right.
Repeat, sir.
Yeah, so
So,
peak to, go ahead.
so basically, you would do this add one peak with the next peak.
Yeah, because this is really one peak is really half of the entire peak to peak.
Mm-hmm.
Yeah, so it would be one peak is just here, but peak to peak would be the entire thing. All right.
Yeah.
So see it right here. No? It's right here. Let me try and zoom in out a bit. Oh my god, that was a bad idea. See it right here. Can you see this?
Yeah. So,
Peak to peak current. So it would be the
yeah.
current from 4 to negative 4. So what would be the peak to peak current?
Positive, what 180 plus 180.
No, I mean the current. We're talking about the current up here. The peak current is 4 ampere, right?
Yeah.
And the peak to peak current is represented here as the highest peak to the lowest peak down here. So what would be the peak to peak current?
Negative 4 plus 4.
It will be the magnitude, use the magnitude. So just like down here, we had 180 plus 180. We don't really consider the magnitude. We're looking at size. We don't really consider exactly where it is. We're looking at the size. All right. So the size of this is actually 180 for one peak and 180 for the other peak. The total thing is 180 plus 180. How much is that?
And 360.
Yeah, so it would be the same concept here. The top peak is 4, the bottom peak is also 4, so it would be 4 plus 4. Peak to peak current would be 8.
So you don't change the sign them when
No, when you're looking at peak
okay.
to peak, yeah. All right, is that better?
Yeah, I'm getting them.
Sorry about that. So yeah, the power dissipated now. One second. It asks for the maximum power dissipated in the resistor. What's that arrow? The maximum power dissipated, you have the formula for power, different power. You have different power. You have trying to expand this. So maximum power equal P equal IV. Remember we did that from the lab as well. And power dissipated. Anyone remember this one? Power dissipated. I squared times R. So what is the maximum current again?
Repeat that, sir.
What is the maximum current?
180.
A 4.
4.
Mm-hmm.
Yeah. Well, the maximum voltage is 180.
Yeah.
So it would be 4 squared times R. R is 45, right?
Yeah.
How much do you get?
$360.
4
720.
squared. Yeah. How much you get?
720.
720. Could someone confirm that?
Yeah.
That is from the 4 isn't it? Yes, sir. 720.
All right. Remember the unit for power is watts. All right. So that's the maximum power dissipated in the resistor. All right. Can I take this down?
Yes, sir.
Yeah.
All right. So we'll just skip through. We'll just run through these quickly. All right. So Albert Einstein put forward a theory that if the energy of a body changes, then its mass also changes. So state the equation which relates these changes, clearly identifying the symbols or letters used in the equation. Anyone remember? Anyone can recall this one? Hmm?
No.
Remember this.
All right. So please, when I give you the answers, please just memorize it as a possibility that will come. All right. So it is changing E equal MC squared. Should I go to Google Classroom for that? Make I see.
Oh.
Give me 1 second. Looking for. All right, so let me bring up that slide. Um, so let me show you where to find it. So Google Classroom, right here. You go to transformers and radioactivity. It is, I believe, somewhere down here. All the way down the bottom. So past radioactivity. This one. Show you the next one. So I posted two of them. I don't see where you will get it. See, Paula say IR squared P equal IR squared, or I squared times R. Let's see it there. I squared times R. Hmm. I'm not seeing where you get radioactivity. Yeah. All right, here it is. So Einstein equation of mass energy equivalence. Right, we did it in class. When nuclei undergo fission or fusion, the resulting nuclei are, as in the radioactive decay, more stable. So anytime you have, well, yeah, you're going to get radioactive decay. What was I saying? You have half-life, therefore you will get radioactive decay. Mhm. So when you have an unstable atom or nuclei, it releases these photons and it releases these radioactive material to become more stable. So you would have energy being released as well, the energy output by a nucleus during radioactivity in nuclear fusion or fission is obtained by a reduction in its mass. So the mass defect is directly related to the energy output. So change in E equal change in M times C squared, where you have change in E being the energy output, change in M being the mass defect, the reduction in its mass, and C being the speed of light, which was 3 times 10 to the negative. All right, so you can find this in Google Classroom. All right. Okay. So that would answer that particular question. The next question asks, let me show you quickly. So go back to your notes as well, please, guys. All right. That I posted on Google Classroom. The next one, state two arguments. Yeah, so that's by stating the equation. Demarco, you have a question? Yeah. Okay. Yeah, so
So, sir,
go ahead.
you're done with I.
I no, we
Yeah.
just did it. Basically, it's the same thing in the notes. What's in
I
the
just
notes?
want formula then.
Yeah, it
Okay, okay.
says state the equation which relates these changes. Clearly identify the symbols or letters.
So change in energy equal mass C square.
Change in MC squared. So yeah, for the 3 marks.
Mm,
So change in E. Anytime you have an unstable nuclei, it will undergo radioactive decay. It will undergo some form of decay. When it does that, its mass will go down. So change in E is the energy released. Change in M is the change in mass or the energy mass defect. And C squared is the speed of light in a vacuum. Simple 3 marks. Sorry for my handwriting. Right, I think my fingers are a little bit numb. All right, so the next question asks for you to state 2 arguments each for and against the utilization of nuclear energy. That is also in the notes. That's like the next slide after that. So it's right here. Bring it up again. So this is Einstein equation. The next one is right here. So pros and cons in using nuclear energy. You have 5. All I need is 2. So I'll go to the ones that I would use. I would not use that one. Let's go through them. Could someone read? Because my mouth is tired. That it's supposed to tired to hear my voice now. So
in the absence of natural disasters, they do not contaminate the environment if car what?
carefully. Sorry about that.
Oh, carefully managed. Okay. They do not produce greenhouse gases such as methane or carbon dioxide or other hazardous gases such as sulfur dioxide or carbon monoxide. Two, when compared to obtaining energy from fossil fuels, fewer lives are lost each year per unit of energy
I find this
produced.
one funny. I find this one very funny. But continue.
But two,
Yeah. Fewer
yeah.
lives are lost. In the energy process, no life should be lost. There's something must be wrong. But no, but you can't live without TV, and you can't live without the internet, and you can't live without light, you can't live without TikTok, you can't live without Facebook, you can't live without Instagram. So people are losing their life just because energy is produced. Come on. That's
Yeah, me get
yeah.
many radioactive materials used in medicine are produced at nuclear power plants. 4. A small amount of nuclear fuel produces an enormous amount of electricity, and therefore delivery and storage of the fuel is relatively cheap. 5. A large supply of U-235 is available.
So this is uranium-235, which is basically essential one that you use in nuclear stations. So you have 5, you just need to choose 2.
Uranium.
Yeah.
Ah,
I would rather you not yawning while the mic is on. Okay. All right, next one. State this disadvantages. All right, so I'm going to ask someone ask to read again if you're able. Disadvantages of nuclear energy. I am tired of hearing my voice already. So I cannot imagine.
Nuclear radiation can destroy or damage living organisms. It can alter the DNA of cells and can produce cancer cells and other abnormal growths.
So that is one.
Staff working with staff working with radioactive materials are irradiated by radious isotopes, which contaminate their surroundings and may contaminate themselves if they ingest a material. 3. Used radioactive fuel still contains radioactive material and is hazardous to the environment. It is usually stored underwater in order to remove the excess heat it produces. The water also acts as a radioactive radiation shield for the surroundings. There is a possibility of catastrophic effects if there is a critical malfunction at the plant. Huge explosion can spread the radioactive material over a large area and the radiation could impact heavily on the plant. Nuclear power stations have to be shut down after several years because the plant and machinery become heavily contaminated. It is very costly and hazardous.
All right. So we see that with every form of energy, you have some drawbacks and you may have some reasons to support it. All right. So that is with nuclear energy. So you can go back to your Google Classroom. It is right here. Transformers and radioactivity. You can go to. As I said, I don't see where transformers are coming because if they said induced EMF would come in, then I would be really worried. So transformers may come, but I'm not seeing. However, still read it through. Spend 1 hour and go through it if you can. All right. We're finishing up now. I think this is the last question that we'll do, even though it's not the last question on the worksheet, but we are way over time. Which one should we do? Um, these are easy. So try and do every question on this worksheet. If you're able to do every question on this worksheet, the good chance that you'll be able to.
Excuse me, sir.
Go ahead.
The question sheet, the classroom, what's up?
Yeah, it's in the WhatsApp. Post it in the classroom.
I see you're gonna put it on YouTube, right?
I'm going to put this session on YouTube. Yeah. Yeah. What should I do? All right. Let's try this one right here. I'm going to do this one and then call it a day. All right. So as I said, nuclear fission is a nuclear reaction in which a moving neutron strikes the nucleus of an atom, splitting it into lighter nuclei, often producing the free neutrons and photons in the form of gamma rays. Remember, photons are just particles of energy, really. All right. Oh, right. So we have uranium, right? Which is the main one that we usually use right here. You see the neutron hitting the uranium, and that causes the nucleus of the atom to split. That gives off energy right here in the form of photons. Anytime it's energy, it's a photons, that's a big word for energy, okay? Literally. So we have barium and krypton, not kryptonite, right? Krypton. So barium, right? Now, oh, all right. Are you hearing me now?
Yeah.
Yeah, sorry about that. The internet went for a second. The extenders are giving problem again. So, yeah. So, how do we calculate A? What would you do?
Subtract the atomic number from. So, um,
But we're missing out something. That's correct. We could, well, not necessarily. Think about it again. All right. So, in the interest of time, remember that all the mass on this side of the equation, all the mass on this side of the equation should be equal to what? All the mass on this side of the equation. So the mass number over here should be equal to the mass number, total mass number over here as well. So what is the mass number over the left hand side?
235
So 235, are you sure that's it alone?
plus 1.
Plus 1.
236.
So 235 plus 1 equal, so mass number should remain the same. Or we could just say is conserved. Mass is conserved. And what is the mass number on the right hand side now?
A plus 90
A plus 90.
plus, yeah,
That's it.
plus 3.
Plus 3. So we see that we have a Newton here, but how much of them we have?
3 of them.
We have 3 Newtons over here. So it will be 3. Do you all see that?
Yes, sir.
All right, so
Yeah.
236 equal to 90 a my a plus 93. So a will be equal to what?
144.
143.
Could someone confirm those, please? I 144, 143, 236 minus.
143.
143.
All right,
Yeah.
minus 93 is equal to 143. And then the next one, the atomic number. What would be the atomic number on the left hand side? The total atomic number on the left hand side.
92.
All right, so 0 plus 92 equal to what?
56 plus Z plus 0.
So Z would be equal to 92 minus 56. That's correct.
Yeah.
So Z would be equal to what?
Boy, 70 man, I'm talking to my last one.
92. This is 36.
John,
36.
36.
36.
Yeah.
All right, where did I lose you, Blake?
funny start, come step out of the room.
Oh, that's not my problem. Man. Next question. All right, so basically what we're saying is that the mass on the left side of the equation should be equal to the mass on the right side of the equation. That's what we're saying. So the total mass over here is 35 plus 1, right?
Okay,
35.
All right.
Well,
While
35.
235 plus 1.
Okay, yeah.
And the total mass over here would, you have 3 neutrons. Each neutron is equal, they have a mass of 1. So the the total mass of all of them would be 3.
Mm-hmm.
Yeah. So it would be 3. So 235, 236, and then we add 90 plus 3 minus, take away 93 from 236, so you get 143 for the mass for A. This will be the mass of this guy right here. Now the proton number for this guy,
Repeat what you say.
last part,
Yeah.
no,
After you said if each something that have a mass of 1.
each neutron right over here
Yeah.
has a mass of
I
1.
1. Yes, sir.
We have
Continue
3
on
of
this
them.
one.
So 90 plus 3, that would give you 93.
Mm-hmm.
And 236 over here as well. You have 235 plus
Mm-hmm.
1. You would take over the 93 and then you get 143.
I'm getting now.
You do the same thing over here, right? Where you have
0 plus 92.
yeah,
No,
and then
all right. And then there's a 56 plus Z plus 0. 56. You put it over there, so negative. Bam, bam, I get to know.
all right, next one. The energy release in the given equation is 1.8 times 10 to the negative 12. Calculate the excess mass in this reaction. All right, so we'll go ahead and use our equation. What is the equation again that we know for the energy and mass? What's that equation again?
E equals MC squared.
All right, so changing E equal to changing M C squared. Remember the changes, please. We solve for changing M. All right, So it would be changing E over C squared. So the change in E was 1.8 times 10 to the negative 12 over C. C is 3 times 10 to the 8. All right, so could someone, so for me, please, 1.8 times 10 to the negative 12 over 3 times 10 to the 8.
Sir, making answer on still
How much I get?
0.00006.
Put it in standard form.
Six times 10 to 5 to the negative 5.
Negative 5.
Yeah.
Mm-mm.
1, 2, 3, 4, 5.
Do over it. Remember that is negative.
12.
How much again?
Yeah, so
Negative 12.
6 times 10 to the negative 5.
How much you get, Turner?
Oh, 6 times 10 to negative 21.
Yeah, sounds more like it. Remember that this is positive 8. All right. All right, next question. I
So
think it's
where you get that?
1.8 times 10 to the negative 12 divided by 3 times 10 to the 8.
Yeah.
So sir, you put in power them.
You have to practice that from now.
Jaja.
Yeah, but practice that from now. You can figure it out in the exam.
So we put
Hmm.
in a calculator. What kind of that?
How much did you get?
0.00006. Let's take that one and get 0.6.10 to the 5.
Hmm.
The negative.
Give me 1 second.
Sir, that's it. That's a 6. Wait, 1, 2, 3, 4, 5, 6, 7, 8. What the heck? E plus 19. What?
Yeah, so you have to learn to use a calculator, right? So how to get 1.8 times 10 to the negative 12.
Yeah. Divide.
Exactly.
These odds, bro.
Oh, see then.
Now divide that by
Yeah. 3 times.
3.
What that man?
3. We're gone. Come on. Three times 10. With H. It starts again. Yeah, that up here. Yeah, I got 6 times 10 to negative 21 as well. Alright?
No, not all right.
Let me show you. I'm going to do it on Google for you. So it was total 1.8.
Mm.
Look for this on your calculator, EXP, or it might come in E. You click that, negative 12 divided by 3 EXP, which will give you times 10 to the whatever, times 6 times 10 to the negative 21. All right, so practice that. Practice using that. All right. The last question for today. Fusion is the joining together of two nuclei. One possible fusion reaction is deuterium plus tritium. That gives you neutron plus energy. So, what is the value of E? That is 2 plus 3 equals E plus 1. You bring over that on the other side. 5 minus 1 equals 4. Next side, Q is 1 plus 1 equals Q. Therefore, Q is 2. So X is 4 over 2. What is this? Nucleus. 4 with a mass number of 4 and a proton number of 2.
Wake up. Hydrogen, sir.
No, hydrogen, I believe, is 1 1. I think. Or 2. I thought I put it. So X is helium.
No, it's
Right?
yeah.
All right, so try and finish the other questions on your own.
Wait, sir.
Hmm?
Go back on the last question there.
This one?
Same one, man. Bro. The last one we just do.
This one right here.
Not even a seed, you know.
Oh, sorry. This one.
Yeah, so like go over it one more time.
The same concepts, right?
Cause two, Monsieur minus if I find in one, I know if I P to the next one or something. No.
This is 2 plus 3 equal P plus 1. So 2 plus 3 is equal to 5, right?
Yeah.
We bring over the 1, it will be minus. So P will be equal to 4.
I'm getting out.
Same concept over here. 1 plus 1 equals Q, because this is 0 right here. So Q is equal to 2. Also,
What?
yeah, Q over this side and 1 over this side. 1 plus 1 over this side.
Cha-cha. 1 plus 1, 2. I get it.
Right there?
Yeah, because you.
So, let me see. Yeah, remember your relationship between mass number, proton number, and so forth. Remember that A is your mass number, Z is your proton number, and N is your neutron number. Right? Neutron number. So remember that the mass number is Z plus N. So if you want to find the neutron number for anything, you just transpose. So A is equal to Z plus N. All right. Is that clear?
Yes, sir.
Final thing, try and go through these questions as well. All right. Please attempt them.
Nem a most man figyekszem, hogy lefelé, nem mondom szó.
All right. So all the best, everyone. You're free to go.
Yes.
All right.